Hello, Math 200 students. Sorry, Math 201 students. Looking at section 2.2, the limit of function and limit laws. All right, in section 2.1, we saw that limits arise when finding the instantaneous rate of change of a function or the tangent to a curve. Here we begin with an informal definition of limit and show how we can calculate the values of limits. A precise definition will wait until the next section. Frequently when studying a function, f of x, we find ourselves interested in the function's behavior near a particular point c, but not necessarily at c. This might be the case, for instance, if c is like an irrational number, like pi or the square root of 2, whose values can only be approximated as close rational numbers. Another situation is when we try to evaluate a function at c, but c leads to division by 0, which is undefined. We encountered this last circumstance when seeking the instantaneous rate of change in y by considering the quotient function delta y over h for h closer and closer to 0. Here's a specific example in which we explore numerically how a function behaves near a particular point at which we cannot directly evaluate the function. How does this function behave at not at x equals 1, but near? That's the key word here. Near x equals 1. So at x equals 1, the function is undefined. We can't even say how the function behaves at x equals 1 because that produces an absurd situation. It produces a situation that is not even possible. But we can say what it does near x equals 1. One way that we could do that is by just simplifying this function. If we factor the numerator as a difference of squares, then we find that the denominator cancels, and so this leaves us with x plus 1. So the function, this function, acts just like this function, except at the precise infinitesimally small point where x is equal to 1. Everywhere else, it is exactly the same as this function. So if we look back here, here's a graph of x plus 1, and here's a graph of x squared minus 1 over x minus 1. They are the exact same thing, except for this little piece right here. That is called a hole in the graph. It's like a little Bermuda point where everything is lost, but everything else is fine. How big is that point? I know when we draw it, we have to draw it with some amount of size, but truly, that point is infinitesimally small. It is of no size. Kind of hard to even think about that. So, how does this function behave near 1? It behaves just like this function. So we could just use this function, and we could say we can get, let's just read this solution here. The graph of f is the line y equals x plus 1 with the point 1, 2 removed. This removed point is shown as a hole, and even though f of 1 is not defined, it is clear that we can make the value of f of x as close as we want to 2 by choosing x close enough to 1. I might say it like this. How close does this function get to the point 1, 2 right here? It gets as close as you can possibly imagine, and then some. Like it can get as close. The only limit to how close it can get to that point is the limits of your imagination. So let's just see. If we look at this chart right here, you can kind of see that. If you plug in 0.9, then it's 1.9. If you plug in 1.1, then it's 2.1. If you plug in 0.99, it's 1.99. How close can we get to the point 1, 2? we can go 0.999999 and get 1.999999, or 1.000001 and get 2.000001, and we can, whatever we can imagine as far as getting close, it can get closer still. All right, generalizing the idea illustrated in example 1, suppose f of x is defined on an open interval about c, except possibly at c itself. If f of x is arbitrarily close to the number L, as close to L as we can imagine, then for all x sufficiently close to c, we say that f approaches the limit L as x approaches c, and you write it like this. The way that you read this is you read it as the limit of f of x as x approaches c equals L, or is L. So we would say the limit of x squared minus 1 over x minus 1 as x approaches 1, the limit of it is 2. All right, it's not actually 2. Like when you plug it in, it's not actually 2, but it is as close to 2 as you can imagine and more. Like it's closer than you can imagine. However much you can imagine being close to 2, it's much more than that. It practically is 2. Like it's hard to even find the language for it. Like limit. The limit is a good word to use. It's good language to use because it's kind of like the only language we have to explain these things that are almost beyond us to even conceive of. Essentially, the definition says this, that the values of f of x are close to the number L whenever x is close to c, on either side of c. So if you go to a little bit to the left of 1, it's going to be a little bit below 2, or if you go to a little bit to the right of 1, it's going to be a little bit above 2. So, if you boil it down to that really simple way to think about it, that this is a good, simple way to think about it. This function value is close to that, close to this limit L, which in this case is 2, when x is close to this value c, which in this case is 1. Our definition here is informal because phrases like arbitrarily close and sufficiently close, or closer than you can imagine, those are imprecise. Their meaning depends on the context. To a machinist manufacturing a piston, close may mean within a few thousandths of an inch. To an astronomer studying distant galaxies, close may mean within a few thousand light years. So it does depend on kind of your context of what you conceive of as close. Nevertheless, the definition is clear enough to enable us to recognize and evaluate limits of many specific functions. We will need the precise definition given in the next section, 2.3, however, when we set out to prove theorems about limits or study complicated functions. More examples exploring the idea of limits. The limit value of a function does not depend on how the function is defined at the point being approached. Consider the three functions in this figure here. All right, here are three functions. In this case, all right, the function is undefined at when x equals 1. Here, the function is defined when x equals 1, but its definition is down here according to this piecewise function. So it is this line until it gets to that precise spot, and then it actually defines itself this way. So the value of g of x when x is 1 is 1. It's the point 1, 1. This function is defined everywhere, including at 1, 2. It's just this line right here. All right. The function f, that's the one in A, has limit 2 as x approaches 1. Even though f is not defined at x equals 1, it's still, the limit of this function is still 2 when x equals 1. The limit of this function is also 2 when x equals 1. It doesn't even matter that when we say when x equals 1, the value of the function is 1. It doesn't even matter what the value of the function is there. It only matters what the function is approaching. Doesn't matter what it is, it matters what it gets close to. So what is the value of the function when x is 1? The value of the g of x function when x is 1 is 1. But the limit of g of x when x is 1, the limit of it is 2. Even though the value of it is 1, the limit of it is still 2. Just like this one. They have the same limit. They have the same limiting value when x equals 1. Just like this one as well. The value of this function when x is 1, the value of h of x when x is 1 is 2. And the limit of h of x when x is 1 is also 2. It just so happens that the limiting value and the actual function value are the same in this case. But even when that's not true, the limiting value does not depend on the actual value of the function. Okay? This is when the actual value of the function is equal to the limiting value of the function. When that's the case, that's a special case that we're going to get into later. That actually is what defines the concept of continuity. This function is continuous at x equals 1 precisely because the value of the function is equal to the limit of the function at that value of x. This one is discontinuous, as is this one at that point. We're going to get into continuity later, but just to introduce the concept to you now, that's what it's going to be. All right. All right, here's just a couple of more like statements rather than examples. But if f is the identity function, the identity function is just y equals x, or f of x equals x, then for any value of c, all you have to do is just plug c in for x, because it's defined everywhere. There's no issues with it going on anywhere. If you plug c in for x, you're going to get c for f of x. So the limiting value is just equal to the function value at c. When x is c, okay, here's that identity function. All right, if we have f of x equals x, and we're saying what's the limit of this thing as x approaches c, well, that means if x is getting close to c, whatever c is, then because this is the identity function, y is also getting close to the value of c on its own axis. And so this thing is getting closer and closer to, the value of this function is getting closer and closer to c. That's just, don't overthink that. Like, that's just kind of obvious. This function is getting closer and closer to the value of that function when x is c, which is just c. All right, next we say, what if it's the constant function? All right, what if it's f of x equals some constant k? Well, the limit of that as x approaches c, what is this thing going to approach for whatever value x is? It's always going to equal k. The function value is always the same thing. It's always k no matter what x is. Y is always k for the constant function. So what is this, the value of this function approaching whenever x approaches c? It's always going to approach k for whatever c you got. It's going to approach k here. It's going to approach k here. It's going to approach k here. It doesn't matter what value of x is because it's always k for the function. So the limiting value is k. So if you just want to look at that, this is just kind of a rule, but it's a rule that's obvious anyway. All right, so what is the limit of x as x approaches 3? The limit of x as x approaches 3 is just plain old 3, right? What is x approach when x approaches 3? It's 3. That's like just an obvious no-brainer. If x approaches 3, then the limit is going to be 3. Here, what's the limit of 4 as x approaches -7, or as x approaches 2, or as x approaches anything? The limit of 4 as x approaches anything is just always going to be 4. The value of x doesn't change this value. It's going to be itself, whatever x is. All right, a function may not have a limit at a particular point. There are some times where the limit does not exist. I don't know if you've ever seen the movie Mean Girls, but that's kind of the classic line in that movie. I don't know that I even remember anything else about that movie. I just remember the moment when she's doing a calculus problem and the limit does not exist is the answer. Some ways that limits can fail to exist are illustrated in this next figure. All right, what is the limit of this function? The limit of this function as x approaches 0. All right, let me get to where I can write on this thing. The limit of this function as x approaches 0. Well, if you get closer and closer to 0 from the left side, then the value of the function is approaching 0. But if you get closer and closer to 0 from the right side, the function is approaching 1. So which is it? Well, you can't say because it's approaching different values from different sides. So it's not approaching one value. It doesn't have one limiting value that it approaches as x approaches 0. Therefore, it doesn't have a limit. The limit does not exist. So a piecewise function like that, where it approaches different things from different sides of that value of x, will be a non-existent limit. All right, what is this function approaching as x approaches 0? Well, because it's a piecewise function, the value of the function is 0. But if x approaches 0 from the left, then we're kind of going this way. And it's just getting closer and closer, like basically it's going unbounded down to negative infinity. But on this side, it's going, if you approach 0 from the right, it's going unbounded up to positive infinity. So which one is it? Well, there's not a single value that the function approaches as x approaches 0. Therefore, it doesn't have a limit either. The limit does not exist. All right. Let's look at this other one. All right, this other one is pretty strange. Sine of 1 over x is actually a function that oscillates. It oscillates faster and faster and more rapidly as you get closer and closer. As x gets closer and closer to 0, this value here just kind of goes to an infinitely high number, and the sine of a billion or the sine of a trillion or whatever it might be, or the sine of a trillion and one, or whatever, is going to oscillate between 1 and negative 1, kind of in an erratic way. Like there's no way, the closer you get, there's no way you can always get close to 0, so there's no way to even say what one value this is going to equal. And so since it oscillates without any boundary to how it's going to oscillate as it gets closer to 0, there's no one value that we can say that function approaches as x approaches 0, and therefore the limit does not exist in that case. All right, these are the same problems in example 4 as we saw graphically in the previous in these previous graphs. These are just algebraically defined, defining those same graphs. And here are the solutions. Why is this one not? Why does the limit as x approaches 0 not exist for this one? We already said it graphically, but we can say it this way: it jumps. When you get to 0, it jumps from one value to another. So if there's a jump there, then the limit doesn't exist. Part B. You might want to just read these if you want to pause it and read these more precise explanations. Part B, we said this already. 1 over x grows too large to have a limit. All right, no matter how close you get to 0, you can always imagine getting closer. And if you imagine getting closer to 0 for x, then you are also imagining the function getting larger. So, and you can always imagine a larger one. So there's no one value then that it approaches. We say that the function is not bounded when that's the case, and so it doesn't have a limit. And we talked about this one. The the way it explains it is it oscillates too much to have a limit. Because the function's value oscillates between 1 and -1 in every open interval containing 0, meaning as you get closer and closer to 0, it's just going to continue to oscillate. There is no one value that it gets closer to. So the values do not stay close to any one number as x approaches 0, and so the limit does not exist. All right, the next thing we have is these limit laws. These should be obvious, and they're very intuitive, simple to know. All right, if you have the limit of a certain function f and being L, and the limit of another function g being m, then you can sum the limits. The limit of f of x plus g of x is just L plus m. In other words, the limit of the sum of the functions equals the sum of the limits of the functions. Likewise, the limit of the difference of the functions equals the difference. The limit of the difference of the functions equals the difference of the limits. And the rest of it's kind of following from there. If you have a function and you just multiply that function by a constant, then the limit of that function is just equal to the just multiplying that constant times that limit of that function. It's just all very, again, kind of obvious, plain stuff. All right. We might want to read this paragraph right here. But you can use that. So look at example 5. So if we want to do the limit of x cubed plus 4x squared minus 3, as x approaches c, we just use those limit rules. But it's really just obvious. Like all you have to do to find the limit of a function as x approaches a certain value is just plug that value in for x. As long as nothing weird happens, you're good. So the limit of this function would just simply be, as x approaches c, would simply be c cubed plus 4c squared minus 3. What about this one? Same thing, just plug in c. It's just going to be c to the 4th plus c squared minus 1 over c squared plus 5. And that's going to be fine because there's actually no way that that the denominator could equal 0, because when you square c, you're going to get a positive number. And then you're going to add something to it, so it's never going to be 0. And then part C, just plug in, as x approaches 2, that just means you're going to plug in -2 for x. And 4 times 4 is 16, 16 minus 3 is 13. So it's just the square root of 13. That's the answer. The only time you can't just plug in the value that x approaches for x is just when something weird happens, like when that exact value makes you divide by 0 or something like that. All right, that's what this theorem states. If you have a polynomial, the limit of that polynomial as x approaches c, it's just going to be plugging c in for the x values in that polynomial. If you have a rational function, p of x over q of x, again, you can just plug in that value, c, and get p of c over q of c, as long as plugging in c to the denominator doesn't make that denominator equal 0. When it does, then you're going to have to do, some extra steps, like simplifying things to see if the denominator could cancel out, stuff like that, little tricks. All right, so the limit of this function as x approaches -1 simply means we're going to plug in -1 into x, and we're going to get 0 on top when we do that, and we're going to get 6 on the bottom when we do that, and 0 over 6 is just 0. So the limit of that function as x approaches -1 is simply 0. All right, notice Theorem 3 applies only if the denominator of the rational function is not 0 at the limit point c. If the denominator is 0, then what you're going to do is we're going to try canceling common factors in the numerator and denominator, which may reduce the fraction to one whose denominator is no longer 0 at c. If this happens, we can find the limit by substitution into the simplified function. All right, an example of that. Here, the limit as x approaches 1. We might just try plugging in 1 for x, but when we do in this one, we're going to get 1 squared minus 1 on the bottom, which turns out to be 0. So you can't, so when that's the case, something weird's happening. It's not defined there. We can't just plug in 1. All right, but what you might be able to do is factor the top, factor the bottom, and see if something cancels out on bottom, and it does. The x minus 1s, if you factored, they cancel. And you're left with this simplified version of that function, which is x plus 2 over x. All right, we can now just plug in 1 into this simplified version and get the limiting value that way. So plug in 1 into here, and you get 1 plus 2 is 3 over 1. So the limit of that function is 3, and you can see that graphically right here, that the original function has a hole right there at 1, 3, but the limit is going to be that point, where that hole is, and where this point of the simplified function is. All right, example 8. Example 8 shows us just like it wants us to plug this into the calculator and get the values in a table, and just kind of show in the table what this function gets closer and closer to as x approaches 0. And it wants us to do it for smaller and smaller increments in the table. So if you make the increment smaller and smaller, it approaches this 0.05. But then if you get even smaller, it seems to approach 0 itself. So sometimes the point of this problem is to say that sometimes you can find these limits like using that approach in the calculator, but calculators and computers can sometimes give false values or misleading impressions for functions that are undefined at a point or fail to have a limit there. So, and that's kind of associated with how the calculator is working to make those calculations, and sometimes it has to do with rounding errors. So kind of, in other words, kind of the most reliable way is to do these things algebraically or graphically. So we're going to evaluate this problem by hand instead of with a calculator. So we're going to have to use some algebra tricks to figure this thing out. And the reason we can't just plug in 0 is obviously because this gives us a 0 on the bottom, which is undefined situation. So let's see what kind of tricks we can pull off here. All right. Sometimes some good things will happen if you rationalize either the numerator or the denominator, whichever one has a radical in it. Try to rationalize that. So since the numerator has a radical in it, I'm going to try to make that not be the case. And I'm going to do that by multiplying by what's called the conjugate of that rational expression, which would be the square root of x squared plus 100. Instead of minus 10, it'll be plus 10. And I do the same thing on the bottom. Then I do all my distributing. I distribute here. Okay, kind of like the FOIL method. And when I multiply this with itself here, I'm going to get just x squared plus 100. So I get x squared plus 100. And then when I multiply this with the positive 10, and then the same thing here with the negative 10, they're going to give me terms in the middle that will cancel. It'll be 10 square root of x squared plus 100 minus 10 square root of x squared plus 100, and they cancel in the middle. So I'm not going to write that down. But then I have negative 10 times positive 10, which gives me minus 100. And this is going to be over x squared times the square root of x squared plus 100 plus 10. So that cancels. So that gives me x squared over x squared times this stuff, x squared plus 100 plus 10. And now what happens is the x squareds cancel. So I think I'm left with 1 over the square root of x squared plus 100 plus 10. Now I can plug in 0 from the limit in the beginning. Plugging in x approaching 0, I'm just going to plug in 0. And if I plug in 0 for x, that gives me just the square root of 100, which is 10. That gives me 1 over 10 plus 10, which is 20. 1 over 20 is the limiting value of that function as x approaches 0. That is the limit. All right, we cannot always algebraically resolve the problem of finding the limit of a quotient where the denominator becomes 0. In some cases, the limit might then be found with the aid of some geometry applied to the problem, or through methods of calculus. The next theorems give helpful tools by using function comparisons. So we have this theorem called the Sandwich Theorem, and it says this. If a function f whose values are sandwiched between the values of two other functions, g and h, that have the same limit L at a point C, being trapped between the two values of the two functions that approach L, the values of f must also approach L. So here's an illustration of it. You have this function f, and in some interval it is sandwiched between h and g. So it's going to be somewhere between the values of h and the values of g, either less than or equal to h, greater than or equal to g. And the stipulation is that h and g both have to have the same limiting value as x approaches c. And if that is the case, then f also has to have that same limiting value L as x approaches c. That's kind of a complicated thing to think about. But the actual problems you'll have to do with that won't be too terrible. In fact, this whole section kind of has some complicated stuff being said, but the actual practice of it is not that complicated. So here's the Sandwich Theorem written formally. All right, the Sandwich Theorem is also called the Squeeze Theorem or the Pinching Theorem. Okay, kind of makes sense. All right, so here's like an example of that. Given that this function u of x is sandwiched between, is greater than or equal to this one and less than or equal to this one, so sandwiched between these two functions here, then find the limit as x approaches 0 of u of x, no matter how complicated u is. So because u is sandwiched between these two, and if I plug in 0 into both of these, I get the same answer. If I plug in 0 to the left third of this whole line of things, I get 1 minus 0, which is just 1. And if I plug in 0 into the right expression, I again get 1 plus 0, which is still 1. So these two sandwich functions have the same limiting value. Therefore, u will also have that same limiting value since it's sandwiched between them. So the limit of u of x as x approaches 0 will also be 1. Okay, Theorem 5. This one seems very obvious as well. If f of x, this function f of x, is less than or equal to this other function g of x for all x values in some interval containing c, except possibly x equals c itself, because that might be, you know, an undefined situation, and the limits of both exist at c, then the limit of f of x as x approaches c is also going to be less than or equal to the limit of g of x as x approaches c. And that just seems, again, rather obvious. All right, and that is the end of the textbook material. All right, let's look at just a few problems from 2.2 homework. Make sure we understand how to do this stuff. So it says we're finding the limits based on this graph graphically. All right, so the limit of g of x, this function, as x approaches 3. All right, here is the point. The question is there one value of the function that the y value or the g of x value is approaching as the x value approaches 3? And yes, there is one point right there. So what is the value of that function, or the limiting value of that function as x approaches 3? It is that value right there, which is 0. All right, part B, now it's the limit as x approaches 8. So here is where x approaches 8, but the problem is here it doesn't exist because there is not one value that the function approaches as x approaches 8, because as x approaches 8 from this left side, it's approaching 1. But as x approaches 8 from this right side, the function value approaches 3. So it doesn't approach just one value as x approaches 8, so the limit doesn't exist. All right, what about 7? All right, here's where x is 7. Is there one value that the function approaches as x approaches 7? And the answer is yes. Both from the left side and from the right side, as you get closer and closer to 7, the value of the function is approaching 0. So that limit would be 0. All right, looking at number 2 now. This function, the limit of this function as x approaches 0, we can kind of see that this is not going to be a simple problem where we can just plug in 0 for x, because that would give us 0 over 0, which is not defined. So we can't just plug in 0. But I think the way I'm going to approach this is, what do I get if I get close to 0 from the left side of the function? From the left side of 0. So like, what's something close to 0? A little bit less than that. So I think it would be maybe negative 0.01. Let's think about it like that. If I plug in negative 0.01 for x, that would give me negative 0.01 over the absolute value of negative 0.01, which would give me negative 0.01 over positive 0.01, which would give me negative 1. Okay, so as I approach 0 from the left side of 0, I get negative 1 as the kind of the limiting value, I think. What if I approach 0 from the right side of 0? Let me think about that. Like, let's let x be positive 0.01. That's really close to 0. So if I put in 0.01 for x over the absolute value of 0.01, that gives me 0.01 over 0.01, which is going to be positive 1. So there is not, I approach two different things, two different function values if I approach x equals 0 from the left side of 0 versus from the right side of 0. So there is not just one function value that we're approaching as x approaches 0. Therefore, the limit does not exist. So let's see how to answer this thing. As x approaches 0 from the left, this thing approaches negative 1. As x approaches 0 from the right, this thing is approaching positive 1. So let's see here. There is no single number L that the function values all get arbitrarily close to as x approaches 0. That's the right answer. Well, let's do number 5. I just want to do number 5 because I want you to see how easy some of these problems are. The limit of this function as x approaches 6. Does anything strange happen when x is 6? Nope. There's no 0 on the bottom, which means all I have to do to get this answer is just plug in 6 for x. That's all I got to do. That will give me the limit. Pretty simple. I felt like number 11 was a little bit complicated, so just wanted to go through that one. If I plug in 8 for C here, I'm going to get a 0 on the bottom, which means I can't just plug in 8. But what I'm going to try to make some simplifications and see if anything good happens, see if anything simplifies. So I'm going to try to get myself a common denominator on top here. So I'm going to try to combine those. So 1 over C minus 1 over 8. I'm just going to get a common denominator, multiply that by C on top and bottom, multiply this by 8 on top and bottom. That gives me 8 over 8C minus C over 8C, which gives me 8 minus C over 8C. So I've got 8 minus C over 8C over C minus 8. Now I'm going to change, flip. Keep that, change the multiplication, and flip that. So 8 minus C over 8C times 1 over C minus 8. Okay, the top here and the bottom here almost cancel each other, but not quite. The only difference here is the signs. What I could do to make that happen is I could factor out a -1 on one of those. It doesn't matter which one. I'm just going to go ahead and factor out a -1 on this part. So if I factor out a -1 here, that makes that 8 become negative, and it makes that C become positive. So I'm going to write it like this. C minus 8, because the C is now positive and the 8 is now negative, over 8C times 1 over C minus 8. And so now these jokers will cancel. So now multiply straight across and I get -1 over 8C. And now can I plug in 8 now for C and nothing weird happens? Yes. So now I can just plug in 8 for C and get my answer that way. I guess that my answer would be -1 over 64. It appears that would be my answer. All right, number 14, I'm just going to think, okay, what if I just plug in 0 for x? Will it be okay? Secant is 1 over cosine. Cosine of 0 is 1. Therefore, it's not undefined. So yeah, I could just plug in 0 to figure out that answer. Same thing on 15. If I plug in -3 pi here, -3 pi plus 3 pi is 0. Cosine of 0 is not undefined. It's 1. So I can just plug in -3 pi into both these x's to figure out the answer here. Here you're just following the limit laws, the limit rules. Since you know that limit's given to you and that limit's given to you, you can just follow those limit rules to figure these answers out. They should be pretty obvious. That one I think you can do. This one is a lot like problems we did back in 2.1. So I'm going to skip that. This is that Sandwich Theorem. So all you have to do is plug in 0 into either the left or the right. And since they're going to come out the same anyway, that's going to help you get your answer. So that's kind of going through enough problems, I think, on 2.2 to help you succeed on that assignment. Good luck on it. I'll see you again in 2.3.